Right, here's another tutorial to go along with homework 3. Right, some of you have asked for a solution to this. Right. And what I recommended was that when you start on this homework problem, like any homework problem, at least my method is I break everything down into simple sub-problems that I can solve. Right, we've already had a couple of videos implementing 2 other parts of the state machine. We're going to implement the part of the state machine in here where we're actually going to generate a signal frequency. So the idea of our homework is that we are going to be sending a signal from Arduino to a Python program using serial communication. And we're actually going to send the signal data. We're going to go ahead on the Arduino side and we're going to create a noisy signal and then filter that signal so that when we get around to using hardware that actually generates noisy signals, we'll already have an example of how to filter on the Arduino side, right? So basically we're simulating a sensor, right? And so what we're going to do here is this section of the Arduino state machine that says transmit signal data. So I've got here is I've started an Arduino program. So this is our test program. My comment is that this is the test for the particular state transmit signal data. Got here in main, we're initializing, we're using the Arduino init function. I'm turning on the serial port at 9600 baud. One of the things we have to do for this assignment is we have to determine what the appropriate baud rate is for the frequency of transmission that we'll need. But we won't deal with that in this particular video. So for our test purposes here, right, we'll just use the 9600. Right. And here in the code, I have hard-coded in a signal frequency. So this variable, right, type double signal frequency, I'm setting it equal to 1 hertz. Right. The idea is I want to break everything down into really simple sub-problems. And I don't want in this section of code to have to deal with anything coming into this program from the serial port. This code is only going to be written to generate the signal, take a look at it, make sure all of that's working, right? It gives us then the basis to use this when we need to integrate this into our final solution, which is why I've now hard-coded it here in this solution. And I'm using 1 hertz. When I want to first generate a signal, so we're going to generate a periodic signal. I just want to generate a signal that's really easy for me to look at visually to have an idea if it's correct. So a 1 hertz signal, we should see 1 cycle in 1 second. Right? That gives me something, like I said, that's visual to look at to have an idea of whether or not this code is generating the correct signal. Right? And so we're going to call a function called generate signal. We'll pass it our signal frequency. This function is just an empty shell right now. And then this program will just go into this infinite while loop, which is basically just going to sit here for 20 seconds. After 20 seconds, it will then call the reset function, right, which was coded up here. What the reset function does is it points program memory back to address 0, which actually will do a complete reset of this and would start this code running over again. Not something that you have to do. Like I said, I like to do this sometimes and make the delay a little bit smaller so I can cycle through the program more than once. And it's just a technique of showing you how you can reset your code if you want to at some point while you're testing, right? Or as part of your operation. Maybe you can't recover from something and you want to reset. But that's beyond the scope of this tutorial. Let's go ahead and fill in our code for generate signal. We want to generate some sort of sinusoidal signal, right? And we're told in our problem definition, the maximum signal frequency will be 250. We need to go ahead and determine a few things like the number of samples we want to take of the signal. Right? Let's start creating some variables. Right? whatever, samples per cycle. I can have. I'm going to say I want 4 samples per cycle, right? So per period. And I'm basing this off of the Nyquist criteria, which tells us that we should be sampling at least twice the highest frequency, right? And so if 1 cycle, right, is the highest frequency, if I take 2 samples from within that, so Nyquist says twice the highest frequency, right? So I'm using cycles instead of frequency. But it gets me the same thing. So I'm going to just put a note here that the Nyquist sampling rate minimum is 2. I mean, just because if I want to come in and change the code later, I want to make sure I don't put it down below 2. Right. Now, for this simulation, because the user, the other program, can send us a variety of frequencies all the way, say, from 1 hertz to 250 hertz, we want to know how much data to generate, because we are actually just simulating a sensor. And we have, in our assignment description, we have something that says that we want to capture some information, plot it, and we want to send an end of data signal. Right? Normally a sensor in our program would just keep running forever. Right? But because we want to send a limited number of data, right, it's up to you as a programmer to decide how much data you will need to plot and evaluate your signal. But I'm going to start with easy numbers that I can visually check. So I'm going to say that our number of cycles is going to be equal to 1 to start with, right? And this is the number of periodic cycles. All right. And from this, right, we can then determine how many samples we need to take to generate then this total number of cycles. Right? So total samples is going to be equal to num cycles times samples per cycle. Right. So that's our total number of samples. And now let's figure out what our sampling frequency is. I'm going to make this a double because our signal frequency is a double. Sample frequency is going to be equal to the signal frequency. And we multiply that times our samples per cycle. And those units would look something like, if you think the fact that signal frequency is in hertz, so hertz is cycles per second times samples per cycle. And you can see then that the unit would then end up being samples per second. All right. So that looks reasonable with a unit check there. And then, right, we're going to have to then have a delta t, right? The amount of time in between samples. Going to be 1 divided by the sample frequency, right? Basically, this is the sample period. The sample period is the inverse of the sample frequency. And this tells us how many seconds per sample, right? Right, because if we're working with a real sensor, we'd only be able to read it at a certain rate. So we have some sort of time interval, delta t, that we would go in and regularly try to read that sensor data. Right, now, we're going to use, it doesn't matter if we use a sine or a cosine, we'll probably just go ahead and use the sine. And when we generate the amplitude of the sine or the value of the sine, we're going to have omega t, cosine omega t or sine omega t, where omega is 2 pi f. the frequency times the time. And what I'm trying to get at is we're going to need a variable for time. I'm just going to call it t equal to time, or we're going to start at time equals 0. So we call that time, right? We can also we're also then going to generate the amplitude of the signal at a particular moment in time. And so this will be our signal value. Right? And we're just going to use the amplitude of a sine wave, that -1 to +1, right? That range. If you want to scale it, you could do so. Like I said, we're just trying to solve this problem at this point in pretty much the simplest way possible and meet most of our criteria, right? We actually meet all our criteria for generating the signal, right? You want to do fancy and add-ons, you do that after you get the basics working, right? And so we're going to have a loop control variable. Now I'm going to have this function just run through, right, and generate all of the samples that we need. So this is going to then take care of that. All right. Now, all right. If we wanted to do a check, say like on total samples, things like that, we could do this and print this out. All right. I need to hook up my Arduino if we're going to implement this. All right. See if we have a reasonable value there. And what we're going to say is while sample count is less than the total number of samples, our amplitude of our signal value, whatever you want to call it, and actually if I use cosine, it doesn't matter. All right, so I need 2 times pi times the signal frequency, right? Because we're trying to generate then this value at our signal frequency times t, right? So 2 pi f is omega times t. Pi, right? Pi is defined in the Arduino .h. This is something I don't normally remember. I'll look it up. Cosine may be defined in Arduino.h as well. If not, I also know it's defined in the math library, so we can put in that math header here. I believe with this showing up like this, that Arduino has gone ahead and brought in some of the math functions that you don't have to bring in math.h. Probably something that I should look up. All right, so we've got our amplitude. Let's just go ahead then and print out some information. I pre-wrote this example so that you don't have to bear with me while I type everything by hand. Right. So we're going to print out the sample count. We're going to print out our value of time. Let's take a look at that as that goes along. We're also going to print out our amplitude. And if we want our loop to not be an infinite loop, right, we're going to add on to time every time by delta t. And I'm going to say sample count plus equal 1. Right, we're going to add on to that. And I'm just going to delay right now by 1/10 of a second between this, right? I'm not worried about the actual simulating the time of the sensor using delta t. That's something that we could go in and fix in a bit. But let's see if this is enough now that we could just generate some information. Right. I'm just going to have to save it. And let's see, I've got warnings and things turned on. So if I go to File, Preferences, right, you can see compiler warnings all. Right, so we didn't have any warnings or any errors there. Let's upload this. And let's turn this on. All right, so now we're in our 20-second delay. So our total number of samples are 4. Right, here's our samples 0, 1, 2, and 3. Here's the time, so it looks like our delta t is a 0.25. The amplitude of our signal, well, we're taking 4 samples within one full period, one full sine wave. So our time's gone by, ran again. All right, and so cosine is 0, should be 1. Cosine, so at 4 samples, the next one would be 90 degrees. This is 0, it's showing as -0 here. Doesn't really make a difference. Then -1, and then 0. So if you were to divide a sine or cosine wave into fourths and go from 0 to 90 to 180 to 270, these would be the values of the amplitude you would expect to see. So this is sort of, right, a quick sanity check, right, of when you run something like this. Do something simple. Don't do the hard one. Don't put this is 250 hertz and then have to try and then put sample 16 and have to try to figure out whether any of those values are reasonable. Do something that you can check, right, manually. That you should have an idea of. Think of this as a test data set, right? You want to generate this, you go ahead and know what it should generate, check to make sure that it did generate it. If it does, right, then we can have some confidence that our code's been written correctly. And now we should be able to do things like, well, we could increase the number of cycles, the number of samples, right? If we increase the number of cycles to 2, we rerun this. Now our total samples are 8. This runs for 8 times, right? Of course, our delta t's, that's going to stay the same. Our amplitude, notice that didn't change, right? Think about why didn't it change? Well, all I did was increase the number of cycles, not the number of samples per cycle. So we still have the same number of samples per cycle. So we're still generating cosine of 0 degrees, cosine of 90 degrees, cosine of 180 degrees, and cosine of 270 degrees. So if we want to see more numbers, we could leave our number of cycles at 2. Let's just put it back to 1. But now let's say, give us 8 samples per cycle. All right, that's old data. All right, so right, we get 8 samples this time simply because we said number of cycles, right? Samples per cycle. We multiply that to get total samples. So still 8 samples, but notice, right? So cosine of 0, our first times 0, angle 0, right, is still a 1, right? But now we're probably getting about 45 degrees in here for the next one, then 90, then 135. Right, so we've got more data points. The more data points we get, the better we're able to recreate our signal. All right, so let's clear this. And let's go ahead and put this on the serial plotter. But if we're going to do that, then can't print out all this other stuff. Right. All I really want to print then is the amplitude. Onto the serial plotter. And if you want, let's run the serial monitor, right, to just show, okay, there are 8 values, right? We're not printing out any extra text or anything. So this should look okay on the serial plotter. And it's probably going to scrunch up our signal a bit because look, it's trying to give us 500 seconds basically. And we've only got the 1 cycle here. So we can't see a whole lot, sort of an up and down line with only, let's see, we're still at, right, 8 samples per cycle, so it's not a bad looking sine wave. Take a look at this. All right, so if Nyquist said only do 2, right, samples per cycle here, right, we plot, we open up the serial plotter. All right, let's look at the serial monitor. All right, we have 1 and -1. It's not very indicative of a sine wave. Now here, so something showed up now, it didn't before. All right, but yeah, it's trying to draw a line from 1, -1. So not very indicative of a sine wave, right? We've taken so few samples, not very indicative. Right. Upload here, if we go to 4. And yeah, I wish there was a zoom feature on this. All right, can't really see much of our signal. Let's go ahead and say that the number of cycles is 8. So we see our signal a little bit better. Now, I wanted the plotter. All right, so that still looks kind of linear, right? With only 4 samples per cycle, we've got 8 cycles there. If you were to bump this up to 16 samples for each period or each cycle, probably be able to draw something that looks a little more like a sine wave with more data points. See, that looks a little more sinusoidal, a little more curved, right? It still has some peaks there, but that's looking better. So the idea is, right, the more we can sample a signal, the better we can reproduce that signal. All right, so at this point, right, we've shown that we're able to generate that signal, right? We've got a serial dot print ln. Now, whether you want to send it as a binary signal, how you're going to handle this, we haven't talked about that, but we have solved, right, in a relatively short period of time. Of course, like I said, I'd coded up this example before, probably spent about a half hour coding the example, checking my units, right, before I started this video. But we could next then go ahead and add the noise signal. Then you can add your low pass filter, print that out. So print it out, transmit it. You might want to decide then what your scheme will be in order to transmit that data. Right? But that is another problem to be tackled separately. All right, so I'll just stop here.